Sun and wind are free. It's the investment in the production infrastructure and its operating that mainly determine the cost of renewables. Is component longevity the real game changer for the price of green energy? So why is it that only innovations or record-breaking new installations grab the headlines? I'm an optimist, but to make the transition we need, we really have to talk more intensively about the lifetime of systems. Hello and welcome to our new episode of minus 253 degrees Celsius, the monthly expert talk that gets to the point, in fact, to the boiling point of hydrogen. Now, today I'm here in the Netherlands, in Tilburg, with an expert for lifetime and degradation of electrolyzer stacks. Hello, Piotr Shifta.
Hello, Keith.
You have a degree in chemical engineering, electrochemistry. Your background is perfectly suited for your role as a product and process engineer. Could you please tell us what the main goal of your work here is?
Here in Tilburg, our main task is electrolyzer stack pre-development. We are working on the next generation of our products. My part focuses quite a lot on stack durability and the degradation topics. I'm trying to understand it in order to make right choices for stack design. And generally, we cannot eliminate aging process, so our focus is on trying to slow it down and minimize its impact. And you have to realize that this is a new product, not only at Bosch, but in the whole industry, which means that the knowledge in this topic is quite limited. There are no industrial standards, there are no official methods to assess the durability, what makes our work not easy.
Well, that does sound very challenging, and I think it's incredibly important too. Isn't this the crucial factor in reducing the production costs of green hydrogen?
It is definitely an important factor, but it's not the only one. We should consider three main aspects. It's the cost of the system, efficiency, and durability. You can imagine it as a sort of a triangle, and the combination of those three results in the levelized cost of hydrogen. So on one hand, it makes sense to make choices resulting in increased durability, but this will have a consequence, likely of increased costs and decreased efficiency. So the real trick is to have a good balance between all those three aspects.
Your job seems like almost impossible task to me. I guess you probably can't run hundreds of prototypes for 5 or 10 years to test and gather data on potential issues. How do you actually approach this task?
Yeah, while cost and efficiency can be estimated, the durability is a more tricky one. It cannot be easily calculated or validated. That's why the understanding of the mechanical and electrochemical processes within the stack is really crucial. To understand it, we have to deep dive to the fundamentals of the degradation mechanism of each component, understand their effects on the system. Some of them will cause performance loss, while others might lead to failure. And the best way to learn about those failures is to experience them. So we try to trigger them on purpose. We use accelerated stress testing in order to achieve results in a reasonable time.
Okay, can you give some examples, some of the components you are focusing on and why?
From a chemical point of view, anode catalysts can be a good example. That's where the actual water splitting is happening. It's exposed to very harsh conditions of high voltage, low pH, and this degradation will have a negative effect on the efficiency of the stack. Another example, maybe from mechanical side, is a membrane. So although the stack looks very robust from the outside, then inside every cell has a membrane, which is in the end like a thin foil separating hydrogen and oxygen, and needs to withstand high temperature, high pressure, and it needs to keep its function for the whole stack lifetime.
Now, what specific aspects do you research to enhance the membrane's performance?
We are stressing it mechanically to determine how much the membrane can withstand, so how easy it is to damage it. And this knowledge allows us to improve the stack design by optimizing the contact of the membrane with its surrounding components to ensure flat, smooth surface, which can provide a good support and minimize the risk of failure.
Could you describe how a typical test is conducted? In my imagination, I can see fields of stacks running in parallel with someone staring at them and waiting for failures, but I'm pretty sure that's nonsense. Can you provide a more realistic overview of your testing process?
We perform tests on different levels, starting from single cells with smaller size, which is more controlled environment. We have multiple specialized test stations able to perform these electrochemical evaluations. We can test specific components, operation conditions, or prepare our intended failure. And we also do tests on the bigger scale with actual stacks with varied size, because certain behaviors can only be observed on bigger size. It's more representative for our final product as well. We don't need to stare at the stacks during operation. We use multiple sensors which help us to see what's actually happening in the system. This data is crucial for the proper evaluation of our tests, model validations, but also this data supported with AI helps to make predictions or translations of the test results into degradation rate in the real life situation.
When I talk to experts, I'm always curious to find out how they would predict the long-term developments in their field for the year 2050. Do you believe that the triangle of cost, efficiency, and durability will see significant improvement by then?
I'm quite optimistic about it. Our understanding in 2050 will have developed a lot, which will definitely make a positive impact on the levelized cost of hydrogen. And I believe that the results of this work will help noticeably to reduce the price gap between the fossil fuels and the green hydrogen.
That's really something you could be proud of, and I sincerely hope your vision becomes a reality. And speaking with you has boosted the reliability of my optimism. Thank you very much. And thanks to everyone for joining us for this latest episode of minus 253 degrees Celsius, the expert talk that gets to the point, the boiling point of hydrogen, and we hope to see you next time.